All right, ready? Well, welcome, good morning. I'm glad you're taking the time to join this session. Before I start, you all got the lucky draw. So you can win a fleece jacket with the OpenMP logo on it. As a special surprise, I got approval to the most active participant will get one too. So then you won't qualify for the lucky draw. We're not going to give two to the same person, but yeah, so if you're very engaged, which is maybe hard for me to decide and I'm biased and whatever, but yeah, so there's going to be two prizes here. So I want to talk about tasking in a very fundamental way. So go back to the basics. What is tasking about? Before I do that, I'd like to know, anybody here used tasking already? No? Yeah, okay. Okay, so that's good. That's exactly the target audience for this talk. So let's get started. So what was missing in OpenMP for a long time actually? That was the following. We couldn't deal well with irregular cases. So basically the compiler would have to see everything. That meant when you would have a while loop, for example, where you don't know how long you will go through the while loop, you could not parallelize it easily. There were ways, but it was really hard. So as soon as you couldn't kind of count things in a way at runtime, then you couldn't use OpenMP anymore. And that was a big missing part. Another part was recursive algorithms. There's nested parallelism, but that's very heavy. So many recursive algorithms are fairly lightweight. So the overhead of the nested parallelism would kill any performance gain you may have. So you could work your way around it. Few people did that. And the solution was ugly at best. That's how I like to say it. So we have a total new episode called Tasking in today's talk. It was introduced in OpenMP 3.0, so a couple of years ago. That means by now it's available in every compiler that supports OpenMP should have tasking available for you. And like I said, it was hard to do certain types of parallelism until that point. Initially, the functionality was very simple by design. The idea was we don't know what we really need, so we'll give you the basic framework, and then as we issue new releases, we'll add what people are asking for. And that's what we see happening now. I will focus on the initial design. For those of you that have some more time, I'll have some slides after the talk. We can go into more detail if you like.
So when you say it was impossible to efficiently implement, that means the overhead was much higher than we wanted to be, and now it's much less?
Right. So the question is, when I say not efficient, is that about the overhead? Exactly. It would work, but it would be really hard to get good performance, especially on higher thread counts. Exactly, yeah. So one comment I would like to make, I could put it anywhere, but you can nest tasks. Well, I would say that's not for the faint of heart. It will work, but you better really know what you're doing. Technically, it is supported. Okay. So what's the basic idea? The basic idea is that you have a thread, one thread, and that thread is going to generate tasks. Actually, the concept is more general than this, but this is the most common use. So you got one thread, it'll generate tasks, and those tasks will be added to some queue. So as that queue gets filled, other threads can start executing. So one will generate the task, and the other ones will say, okay, the task is ready, I'll start executing it. That's a very crucial step in the whole model of tasking. Okay. So keep that in mind as I go further. So who does what and when? Your task is to find pieces of code that are independent. And again, you'll see examples soon, but you have your application, you have code blocks, and you know they can be executed independently. That's when you can use tasks.
The user has to be responsible for making sure that there is no risk.
Exactly. So the question is, the user is responsible for getting it right. Yeah, that's true. That's true in general for OpenMP, and there's no exception here. You have to make sure that whatever is called a task can execute with another task for that same code block in parallel. No side effects. No sneaky modification of shared variables without having a critical region. Yeah, question?
What seems to be a bit hard to evaluate is how to balance, to do work balance. You're the master who generate thread that generate the task. You need to generate enough task for the other person.
Yeah.
Will you talk about insights about how to evaluate
No, let me repeat the question, and the answer was simple, no, but the question is, how about the load balancing of all the tasks? That's one of those high-level design choices to not give you that control. The runtime system is supposed to do the right thing always, and we know that's not the case. Okay, let's be fair about it. We know that's not the case, but it's an incentive for runtime systems to improve. So there are actually very different queuing strategies, and that's an ongoing field of research in people doing runtimes for OpenMP. So, will we have control in the future? Maybe. That's why and then you have to wonder about what. How do you expose that? How ugly is it going to be? So it's certainly a point of attention, but right now you don't have any control, and we do know different runtime systems behave in a different way. Okay. Sometimes good, sometimes bad.
So going back to the task queuing. So if I say give a certain number of tasks, but the system determines that that's not optimal number of tasks, I need to go to an alternative path, or does it tell you no tasking?
Yeah, you're basically asking how smart is the runtime system. It really depends. So there's already different queuing strategies. Who are you going to assign work to? And there's a lot of improvement going on right now. So initially, the weak point of this was the efficiency of the runtime. And we see huge improvements as time goes by now. So, yeah. But basically, right now, you cannot make any assumption who does what. Okay. There's things like affinity. How does that translate on a CC NUMA machine, for example? Again, the hope is that runtime systems are clever enough to do that. And I've been around long enough to know that that's not the case, But it may get there. That's the thing. So, all right. So that's the only thing you need to do in your program. And then, as I already said, here's what happens. Your program executes. The runtime will encounter a task construct. It will generate the task. Only generate. It is a little bit like a malloc. When you do a malloc, you tell the OS, I want some memory. And later I'll be using it. It's a kind of similar to that, because nothing may happen at that point, because the decision when to execute a task is really up to the runtime system. Again, that's outside of your control. So it can be immediate, it can be delayed. Both can happen. Some tasks may start immediately, other ones will be delayed. So there is one thing though, you can enforce when tasks should be completed. So you can tell, and you'll see that in a minute, you can tell now I want you to complete all children tasks. Yeah? Multiple instances of the same task? Well, there has to be, yeah, sure. Yeah. It's whatever you embed in a Pragma OMP task will be done. Yeah. So, yeah. So, yeah, you can have the same task, kind of. Yeah. So, this is all you need to do, is embed that code block, use the Pragma OMP task, or in Fortran, declare it to be a task to the system.
You have to specify how many tasks?
No, you can't. You can't. I'll get back to that. Yeah. Okay. So, how about the, oops, sorry for that. There are two task synchronization constructs. So this is when a task synchronization point is when you force the system to complete all children tasks. It's like you're going to preempt the queue. And one is in the barrier. So each time you have an implied or explicit barrier, tasks are going to be executed. Yeah.
What if it's inside of this section?
As soon as you hit the barrier, the task, the pending task, will be completed. Yeah, so the question is, well, how about the nested section? Yes, indeed. Whenever there's a barrier, tasks still pending will be executed.
No matter where they are, all the tasks that are being scheduled to hit that barrier.
Yeah, it doesn't matter where they are. Okay. As soon as the run, it's a very simple concept. As soon as the runtime hits the barrier, they'll start executing the tasks. Whatever is pending still. Okay. So could be in a section, could be at the end of a parallel region, as soon, or you put in a barrier yourself. So doesn't matter. Yeah. The other point is, because it's not always, you don't just want to sprinkle barriers to complete tasks. That's not a good idea. So there's the task wait. The task wait will wait for all pending children tasks to be finished. Okay. So again, that's when you preempt the queue, and after that you continue. Okay.
Is that synchronous or asynchronous construct?
Is that synchronous or asynchronous? That's definitely synchronous. You're going to wait. You're going to wait for the task to be finished. Yep. Yep.
Is there a difference between the barrier and the task wait?
Well, the question is there a difference between the barrier and the task wait? Absolutely. The barrier is still the barrier. So that's why you can't just only have the barrier, because you wouldn't like to add a redundant barrier to complete your tasks. Okay? So that's why you have the task wait. So you don't have the overhead of a barrier, the implications with the barrier. So you definitely need your own construct. This is like a safety net. This will just make the whole system easier. And yeah. What? I don't know what's happening here, but okay. So I'll have one example. And for a while I was struggling with giving you the simplest of simplest examples to show you how tasking kind of works. Because people used to start with something too complicated, I think, and you get lost in the details. So this is admittedly very simple, and it's going to be a little bit of audience participation time. I will ask some questions, and feel free to answer or just totally ignore me. This is recorded, by the way. This will show up on the website one day. I don't know what will happen with the editing phase. Okay, so your task for today is write a program that either prints a race car or a car race and maximize the parallelism in that assignment. Okay, so we write a very simple program to print, with 3 printf statements, a race car. All right. So, no-brainer question: what will this program print? I'm not even going to wait for answers. So, all right. So, it will print a race car. All right. I could run this in parallel and embed it in a parallel region. Okay. Now it's going to be funny. Anybody daring to try what this will print? Exactly, any combination of this, as long as you obey a race car. Okay, I hope that's clear. It could be AA race cars. It could be very funny English. So, and not being a native English speaker, I can relate to that. So, although it hopefully won't be as bad as that. All right. So, but that's not. We don't fulfill the assignment. That was not the question that was being asked. We should still print a race car or a car race. Okay. So theoretically, indeed, you can get all these combinations. All right. Well, we could cheat and put it in a single, and then again, we're back to a race car, but now we don't have parallelism anymore, so that will be rejected by the committee. That doesn't qualify, all right? So you get this, you compile and run, and you get a race car, but that's cheating, so yeah. Of course, tasking. That's the answer to this, to solve this problem. So what I do, I make each print here. So I always want to have A, okay? And then I'll have race and car being a separate task. Oh wow, okay. So I hope that's clear that this does what you like it to do, because the task will be executed independently. So whoever comes in first will do the job. So we have race car or car race. Anybody daring to guess what this will print? You see, now it gets harder. Now it's get quiet. Okay, we're on a tight time schedule here, so it'll actually don't print what you expected. The A will come last. Okay, because the tasking, sorry, the A will, yeah, the tasking will print either car or car race. Yeah. All right. All right. So you did well, but as in good tradition, you get punished for a good deed. You did well, so now I want to do more. I want you to extend the program and print a car race or race car is fun to watch. All right. So, and as usually teachers like to do, they give you a useless hint. Use a print statement, which is absolutely obvious. So, all right. So, okay, I'll add is fun to watch. Now this is going to fail. Right. This is going to fail because this is the way I read it, but that's not how it's executed, because these tasks will be deferred. They will be deferred, and they'll be printed in the first barrier, which is going to be the single has an implied barrier. So what we'll see is first A is fun to watch, and then car race or race car. Now it's truly broken English, and we don't get what we want. So indeed, when you run it, that's what you get. So you absolutely need the task wait to make sure that you first get that part of the print, and then you continue. All right. So now we have the whole thing, and that basically completes this tutorial. Again, I have some more slides, but the idea is to keep this tutorial in this length. So if you want to hang around, have more questions, definitely. There is a lucky draw, but first I get to give. Oh, did you? There's some issues with tasking. Of course, this was a very simple example. I didn't talk about the data environment. That's a fairly complicated part, because how do you get data into a task? By default, everything is first private. So you can change that, of course. First private makes sense. Another thing is, typically when you have a recursive algorithm, it gets smaller and smaller as you go down your recursion. And what can happen is that the amount of work is so little that the task overhead will kill you. That's why there's the final clause when you say stop generating tasks. Just start executing. Don't generate more tasks. Just keep on executing. So that's like a fine-tuning. Before we had that, this is in 3.1. Because before we had that, people would use ugly if clauses and whatever. So. The other one is, because of the data environment, each task inherits the data, or part of it. So when you have thousands of tasks, you can need a lot of memory. So that's when you start, well, merge them. Merge the data environment. Don't add more data to it. Okay. So those are fine-tunings to control the performance and the memory usage. Here's my example, more complicated, but more real life. That's going through a linked list. So let's say I have this while loop, and I call some function, and it gets an entry from the linked list, but each entry represents independent work. So I could do them in parallel, but this is a very sequential process. I go through that linked list. You could do that in the ugly style. You could count all the iterations and then build a for loop out of it, but you could scan your linked list and then build a for loop. That's really ugly, and nobody did that. Right. So that's what this said. So here's the OpenMP code, and let me run you through it. We have the parallel region, right? And again, this is a sequential process to generate the tasks. So I put it in a single. which is really funny when you look at it, parallel single, like that doesn't seem to make much sense. It makes more sense with tasks. So one thread will encounter the single and will start executing this. All other threads will skip it and they'll start waiting in the barrier here. That means they will start executing the task that the other thread is generating. All right? Yeah?
The number of threads that you have available to do the tasks is defined by the number of threads?
Yeah, any regular way of OpenMP to set the number of threads will be used here.
So if I set it explicitly after parallel, use those number of threads.
Right. So you can just set that here, num threads, whatever, and whatever -1 will start executing the tasks. And eventually, if this one is finished, it will also start executing its own tasks.
OpenMP single doesn't imply a barrier?
No. Yes, it has. The single has a barrier. So the task will be executed here, not here. So in the next version that I'll show, I have a no wait because I don't like having two barriers. Well, let me show that one. So the right way to do it would be to have a no wait here, so they'll get executed here, not here. Okay. You don't want to have too many barriers. Yeah, right. So I wish I had another fleece jacket for you. It's a good question. So, but yeah. So what's happening here is that these tasks will be generated only again. So they'll grab, when you look at the full code, they'll grab an entry from the list and do some work. So now I have all these entries being generated and they'll be executed. So the first time I saw this is not counterintuitive. The second time it's less non-counterintuitive, and by the third time you get it. But it's some sort of template of how you do this. I didn't put that on the slides here, but there's other templates for like recursive functions, somewhat different. But yeah, so the idea is the same. I think that was my the last one. So what's new in 4.0? The two main extensions are dependencies. Now you can say this task should only execute it when the other ones, when this group has finished. That's, I think, a useful addition. Not everybody will need it, but it was clearly missing in the sense that, like I said, we want to keep it simple, and this was clearly needed, so it has been added in 4.0. Likewise, you can talk about this task group. You can group tasks. And actually, when you have the task wait, it will only preempt direct children, not whatever those might have generated. All right. Now they'll complete all of them will complete. That's a less frequent scenario. I think the depend is very useful. This one is definitely useful, but for a smaller audience than depend probably. So that's good. That's on your way to you. I don't know for you, those of you in the BOF yesterday, compiler people are busy typing it all in and having 4.0 available. So I don't know, within 6 months I think you'll start seeing first 4.0 compilers being there. And a year from now I think we'll all have 4.0 compilers.
For the depend clause, why
Yeah.
couldn't you do a task wait to finish all the previous code, start again?
Yeah, right, yes. So, well, depend is, you not necessarily want to have all the tasks finished, but when you think of, for example, some sort of pipelined approach where you say, well, I won't start until you have completed this work. You can't do that with task wait. Is very brute force because everybody will complete. And maybe, yeah, so maybe only if a part of the work has been done, some other task can continue. So you can be more selective. Yeah, right, yeah, so, what?